Okay, the title of my talk is Role of Criticality of Gene Regulatory Networks on Emergent Properties of Biological Systems. This is what I did for my doctoral study at the State University of New York. In my studies, there are a few technical terminologies, so I prepared a couple of slides for better understanding of my studies. What is a gene? A human body is composed of numerous cells. In the cell, there is a nucleus. In the nucleus, there are chromosomes. In the chromosomes, the chromosome is made up of DNA. A gene is a section of DNA containing the code for making proteins, the building blocks of life. What is a gene regulatory network? Here, gene A, if gene A is activated, then it makes a protein. This protein influences the activity of gene B. If gene B is activated, it makes another protein. Simplifying this process, we can say gene A influences gene B. A gene regulatory network is a collection of genes that interact with each other. Then what is a Boolean network? A Boolean network is a simplified gene regulatory network model. In this example, gene A and gene B activate gene C. Gene C inhibits gene B and gene D. Gene D activates gene B. So a Boolean network represents those relations between genes very simply using Boolean operators such as AND, OR, and NOT functions. In this example, if gene A and gene B, both of them are activated, then gene A and gene B, they can activate gene C. So we can express it like this: C equal A and B. Let me talk about Boolean networks in more detail. A Boolean network was suggested as a gene regulatory network model by Stuart Kauffman in 1969. He used NK Boolean networks, also known as random Boolean networks, to investigate the dynamics of gene regulatory networks. Here, N is the number of nodes. K is the number of input links per node. One node is assumed as a gene. The state of node can be 0 or 1, inhibited or activated. The state of a node can be updated by the input nodes and assigned Boolean functions. This is an example GRN. And here, N is 4 because there are 4 nodes. And K is 2 because each node has 2 input links. The assigned Boolean functions to each node are as follows: OR, OR, NOR, AND. For example, gene 1 has 2 inputs, gene 2 and gene 3. So gene 2 and gene 3 is our inputs. Now the assigned Boolean function is OR function. So if the states of gene 2 and gene 3 are 0, then the state of gene 1 becomes 0 at the next time step. For the rest of the cases, gene 1, the state of gene 1 becomes 1. The state space of a gene regulatory network is a set of all possible states. This is an example GRN. There are 4 nodes, so all the possible gene expression values is 2 to the power of 4 is 16, from 0, 0, 0, 0 to 1, 1, 1, 1. As I said in the previous slide, If gene 2 and gene 3 are 0 at time equal t, then the state of gene 1 becomes 0 at the next time step. So based on the assigned Boolean functions and input nodes, we can complete. If the initial state is 1, 0, 0, 0, then it goes into 0, 0, 0, 0 at the next time step. In the state space, we call the stationary state, the repeated states, we call these states attractor. We call the other states basin of attraction. Depending on the structure of state space, the phases of gene regulatory networks are divided into 3: ordered, critical, and chaotic regimes. By adjusting node in degree k, the phases of germs can be varied. K equal 1 is ordered, K equal 2 is critical, and K is larger than 2 is chaotic on average. Let me talk about my studies. The relationship between criticality of gene regulatory networks and dynamics of gene regulatory networks was actively studied at a single cell level. But however, the relationship between criticality of gene regulatory networks and properties of multicellular organisms has not been fully understood yet. So we aim at revealing potential roles of the criticality of gene regulatory networks at a multicellular level and a hierarchical level using random Boolean networks as gene regulatory networks. Specifically, we perform 3 studies. Firstly, we investigate how the criticality of gene regulatory networks affects the pattern formation. In this study, we use a morphogenetic model. Here, morpho means the pattern or shapes. The genetic means the formation and creation. So a morphogenetic model is a model creating a shape or a pattern. In a biological viewpoint, our morphogenetic model can be considered as a model showing, creating patterns, diverse patterns like tissues and organs in human body. Secondly, we examine how the criticality of gene regulatory networks affects the pattern formation in the presence of mutations. We use the same model and we add genetic perturbations to gene regulatory networks. Thirdly, we investigate how the criticality of gene regulatory networks affects the robustness and evolvability of multi-layer gene regulatory networks. This is the first study. Our morphogenetic model starts with one seed cell and grows into cell aggregation. All the cells have identical random Boolean networks as gene regulatory networks. This is a movie showing a morphogenetic pattern. Sorry. In our model, there are 4 cell phases: proliferation, differentiation, apoptosis, and quiescence. A cell expressing proliferation can be divided into 2. A cell in differentiation is labeled as differentiated. A cell in apoptosis dies and disappears from the space. A cell in quiescence does not show any cellular behavior. To understand our morphogenetic model, you should know 3 parts. One is GRN. Another is the cell signaling mechanism for cell-cell interactions. And the other is the spring mass damper kinetics for cellular movements. Firstly, a gene regulatory network. We randomly assigned 4 cell fates to the attractors of gene regulatory networks in the order of proliferation, differentiation, apoptosis, and quiescence. In the case of the quiescence, it was repeatedly assigned over 4 attractors. We used in 16 nodes in actual simulations. Secondly, cell-cell interactions. In the gene regulatory networks, genes are composed of normal genes producing signaling molecules and receptors. The genes producing signaling molecules and receptors are matched one-to-one. This is on the basis of specificity in signaling, by which certain signaling molecules can respond to the particular receptors. The cell signaling mechanism is divided into 2, autocrine and paracrine. Autocrine is cell signaling where the receptors are influenced by signaling molecules the cell itself produces. The paracrine is cell signaling where the receptors are influenced by the signaling molecules neighboring cells produce. When there are no neighboring cells, autocrine is used. And when there are neighbors, is used in our model. The states of the receptors are determined by the average concentration of the signaling molecules of the neighboring cells, which caused the change of gene state. So transitions between cell fates occur by the changed gene state. Thirdly, cellular movements. We used spring mass damper kinetics for cellular movements. Each cell has the cell position x, y in Cartesian coordinate system. The edges connecting cell centers are modeled as springs with spring constant K and spring equilibrium length L. And for viscous resistance, dampers with damper coefficient C were included. Through the spring mass damper kinetics, the physical interactions, the repulsion and adhesion occurs in our model. So this, the repulsion and adhesion allowed the cellular movements. To get more diverse shapes of patterns, we used different parameters values of spring constant K and spring equilibrium length L and constant damping coefficient C, depending on cell fates between cells. All the possible cell fates between 2 cells are categorized in 6. In addition, we added small perturbations to the updated cell positions. We conducted 10,000 independent simulations to see if there were significant differences among each group, K go 1, 2, 3, 4. Whenever each simulation run was terminated, we captured the pattern, representative pattern at the final time step. So we obtained 10,000 patterns for each K. We used 12 measures for pattern analysis. First, number of cells. Second, average distance of cell from center of mass. Third, average pairwise distance. Here, the pairwise distance is the distance between each pair of cell positions. The fourth, callback labeler divergence. Fifth, mutual information. Let me talk about the callback labeler divergence and mutual information in more detail. In a morphogenetic pattern, we randomly sampled 2 points, and then we calculated the Euclidean distance from Euclidean distance between them. And from iterating this process 10,000 times, we got a pairwise particle distance distribution. Similarly, we got a pairwise particle distance distributions from a random pattern. Based on the two distributions, we calculated the callback labeler divergence. In our study, the callback labeler divergence quantifies how non-trivial morphogenetic patterns are compared to randomly distributed patterns. So the larger callback labeler divergence is, the more interesting the shape is. In our model, the mutual information examines nonlinear correlation of cell fates between neighboring cells in a morphogenetic pattern. So the larger mutual information is, the more cells interact with certain labels. To apply measures related to a network topology, we constructed a network each pattern. We connected each cell to the other cells within the neighborhood radius R. So the six. Actually, this the such network construction let us know the topological differences for each K more effectively. Specifically, sixth, average clustering coefficient, seventh, link density, eighth, number of connected components, ninth, average size of connected components, 10th, homogeneity of size of connected components, 11th, size of the largest connected components, 12th, average size of connected components smaller than the largest one. These are the results of the 12 measures. When seeing the number of cells, the values decreased as K increased. These trends was also shown in most of the measures. However, the mutual information and callback labeler divergence showed completely different trends. Both of them were largest at K equal 2. The callback labeler divergence was largest at K equal 2. This means the non-trivial morphogenetic patterns were generated most frequently at K equal 2. So we can say the criticality of genome regulatory networks facilitates the formation of non-trivial morphologies. In the case of mutual information, I will talk about it in the next study because the analysis is overlapped. These are the morphogenetic. These are randomly sampled morphogenetic patterns for each K. As you can see, the patterns at K equal 2 look like more interesting. Here. This is the second study. In the first study, we included all kinds of randomly generated systems. However, biological systems are products of evolution. So sorry. The biological systems are a product of evolution, and therefore the results of the first study may have been affected by the biologically relevant data. So in the second study, we assumed that the biologically relevant gene regulatory networks were robust and evolvable. Based on this criterion, we filtered the irrelevant, biologically irrelevant the GRNs. Specifically, we perturbed the gene regulatory network in the seed cell. We added, deleted, or switched one regulatory link between a pair of genes. All the cells had the same perturbed gene regulatory networks because the cells were duplicated through cell division process from the perturbed gene regulatory network. Against the genetic perturbations, if the gene regulatory network conserved the existing attractors and simultaneously the gene regulatory network created new attractors, we considered the gene regulatory networks as a robust and evolvable gene regulatory network. Here we focused on analyzing patterns made from robust and evolvable GRNs. These are the probabilities of generating robust and evolvable gene regulatory networks for each K. We found that the robust and evolvable GRNs were generated with the highest probability at K equal 2. These are the morphogenetic patterns from robust and evolvable GRNs. You can see the greatest number of the patterns at K equal 2. The robust and evolvable gene regulatory networks were generated with different probabilities for each group. So we applied 1,000 bootstrap sampling to the values of the 12 measures for comparison between groups with unequal sample sizes. These are the results of the 12 measures. First, when seeing the number, this is a correlation matrix between 12 measures. So when seeing the number of cells, the following the measures were highly correlated to number of cells. Look at this number of cells. The values at K equal 1, 2, 3 were similar, but fell sharply at K equal 4. This trend was shown in the measures highly correlated with the number of cells. However, the number of connected components, mutual information, homogeneity of sizes of connected components, callback label divergence, and link density showed completely different trends. From those five measures, we could find the interesting results. Firstly, the callback label divergence was largest at K equal 2. This is the same result with the result of the first study. So we can say the role of the criticality of gene regulatory networks maintains even in the presence of evolutionary perturbations. Secondly, the mutual information. The mutual information was the largest at K group 2. It means the fate of a cell was strongly correlated with the fate of its neighboring cells in the patterns at the criticality. So we can say the certain combinations of cell fates between neighboring cells occurred most frequently. From the homogeneity of sizes of connected components, their link density, and number of connected components, we found the interesting topological property. K-1 had the relatively higher homogeneity of sizes of connected components and lower link density and lower number of connected components when compared to K equal 2, 3, and 4. So we express it as just high, low, low. So K equal, similarly, in the same order, the K equal 2 showed high, 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 and K equal 3 showed low, high, high, and K equal 4 showed low, low, low. Based on these values, we found the overall topological properties for each K. The patterns at K equal 1 were composed of the homogeneous large size connected component, which had like a long chain. The patterns at K equal 2 were composed of the homogeneous size connected components where cells were interconnected. The patterns at K equal 3 were composed of the heterogeneous size of connected components where cells were interconnected. Lastly, the patterns at K equal 4 were composed of the heterogeneous small size number of connected components which had a shape like a short chain. In our morphogenetic process, there is a feedback relationship. Cell-cell interactions determine a cell fate. Depending on cell fates, the spring mass damper kinetic parameters were applied. By the spring mass damper kinetics, the cells were positioned, and the cell positions influenced the number of neighbors. So in this feedback relationship, how topologically homogeneous cell clusters appeared at K equal 2. Because the parameter values of spring mass damper kinetics depend on the cell fates, the more frequent certain combinations of cell fates are, the more likely to be applied the same parameter values of spring mass damper kinetics are. So the most frequent combinations of cell fates would naturally produce more topologically homogeneous cell clusters. Our findings correspond to an epigenetic viewpoint that heterogeneous and complex features emerge from homogeneous and less complex components through the interactions among them. Our study showed the non-trivial morphologies were produced most frequently when GRNs were critical, typically with topologically homogeneous cell clusters. So our findings support not only support the epigenetic theory, but also implies that the highly structured tissues and organs might stem from the criticality of gene regulatory networks. This is the third study. In the first and second studies, we used a particle-based warp-genetic model where cells continued move by spring mass damper kinetics. So it's not easy to assess the robustness and evolvability of the whole system. So here we present a more formal hierarchical network model and investigate the robustness and evolvability of the whole system at a hierarchical level. Our multi-layer GRNs consist on intercellular and intracellular layer. Intercellular network, this is intercellular network. All the cells have the same intracellular gene regulatory networks. In actual simulation, the number of the intercellular networks was 9, and the nodes of intracellular networks was 6. Our multi-layer GRNs are divided into 2 types depending on cellular topologies. The multi-layer GRNs with static cellular topologies have fixed cellular topologies like this in all the simulation runs. The other is the multi-layer GRNs with dynamic cellular topologies. They have cellular topologies that are randomly changed in each simulation run. The dynamics of multi-layer GRNs are determined by neighboring cells and the dynamics of intracellular GRNs. Actually, this is similar to the updates of our morphogenetic model in the first and second study, so I just this slide. To measure the robustness and evolvability of multi-layer gene regulatory networks, we perturbed an intracellular gene regulatory network in one of 9 cells. As the result, different intracellular GRNs came to exist within one system consisting of 9 cells. Here's a question. The perturbed intracellular GRN is robust, then is the multi-layer GRNs robust as well? To answer the question, we investigated the relationship between the properties of multi-layer GRNs and intracellular GRNs. Against the perturbation, if the existing attractors were conserved and simultaneously the new attractors were created, then the gene regulatory network was considered as a robust and evolvable gene regulatory network. If the existing attractors conserved without new attractors being created, then the gene regulatory networks was considered as a robust gene regulatory network. And if the new attractors were created without the existing attractors being conserved, then the gene regulatory networks was considered as evolvable gene regulatory network. The gene regulatory network, which did not belong to any categories above, then was included into this category. So we assigned integer values to the 4 categories in the order of the 4, 3, 2, and 1. So using the integer values, using these integer values as x, y Cartesian coordinates, we made a 3D histogram. The property of perturbed intracellular GRN versus property of a multilayer GRN versus frequency. These are the probabilities of generating robust and evolvable multi-layer GRNs and intracellular GRNs in static and the dynamic cellular topologies. All the values were highest at k equal 2. This means the criticality of intracellular GRNs yields maximum robustness and evolvability at a single cell and hierarchical level for both static and dynamic cellular topologies. To investigate the relationship between properties of multi-layer GRNs and intracellular GRNs, we calculated correlation coefficients. All the values were smaller than 0.17. So it means there are almost no correlation or a very weak correlation between the properties of multi-layer GRNs and intracellular GRNs. That is, even if the perturbed intracellular GRN is robust, the multi-layer GRN can be not robust. So the robustness and evolvability of multi-layer GRNs must be understood as emergent properties at a hierarchical level. These are the probability of generating robust and evolvable multi-layer GRNs, depending on number of links of an intercellular network. As the number of links of an intracellular network from 10 to 8, the probabilities did not monotonically decreased or increased, but fluctuated. In addition, the values were higher at k equal 2. And especially the value that reached the maximum when the number of links of an intercellular network is around 40. That is, the link density is 0.5. So this means the degree of interactions between cells can maximize the generation of robust and evolvable multilayer GRNs by amplifying the effect of the criticality of GRNs. Based on the 3 studies, the criticality of gene regulatory networks, we can conclude that the criticality of gene regulatory networks facilitates the formation of non-trivial morphologies at a multicellular level. And we can say the criticality of GRNs promotes the generation of robust and evolvable multi-layer GRNs at a hierarchical level. Our findings demonstrate that the roles of the criticality of gene regulatory networks are hard to discover through the single-cell level studies. So that's the reason why we needed to study on the criticality of gene regulatory networks in the context of multicellular settings. Our study have limitations. We developed artificial models using random Boolean networks as GRNs. So we are planning to develop more biologically plausible models. For example, for morphogenetic model, we use the metabolic Boolean network of a cancer cell, and we can add the microenvironmental factors such as the nutrient or the oxygen gradient. Then we could explore the relationship between the properties of a metabolic Boolean network of a cancer cell and morphologies of cancerous cells. So for example, for multi-layer giants, we use Drosophila segment polarity network. Then we can investigate the robustness and evolvability of the segment polarity networks in real biological systems. So if you have any ideas for applications, or if you would like to collaborate with me, then please feel free to contact me. Thank you. That's it.
Thank you very much, Kevin. Are there any questions? Hi. In the kinetic model, how you move the cells, are all cells connected with each other, or how did you decide which cells are neighbor of each other?
We said neighborhood radius R. So if some cells are within the neighborhood radius R, we consider it, yeah.
And it's the same radius you consider to build up the interaction networks after? Because you then at the end to analyze the final state of the system, you build a network between cells. So you use that same distance to
same distance,
right? Yeah. And that distance, how did you decide how big R should be?
Through iterating the several simulations, we empirically decided the values.
So you use the R that made the most interesting patterns or something like that, or?
Sorry.
So you say that you empirically decide that the value of R, but on which basis? Which was the deciding factor, or how do you really decide this R will be the one we will use?
Actually, in my model, there are a lot of the parameters. Spring mass temper kinetics parameters, for example, spring constant K, spring equilibrium length L, the damping coefficient C. So there are a lot of, because there are a lot of the parameters, we had to consider all the parameter values. So considering all the relationship between them, we empirically decided.
Thank you. Yep. ¿Tú? Tienes el micrófono.
Okay, I have a comment. This is not just a question, it's more like a comment. Criticality in these systems is well defined when the system is very, very large, when the network is too big. Actually, criticality is a property that is defined in the thermodynamic limit, in which the size of the system goes to infinity. Of course, in reality, there are no infinite systems out there. All of them have finite size. But I think that in this type of networks, this property, criticality, can be seen very clearly for networks with 20 nodes or networks with 15 nodes. Well, you start to see this property. But networks with 6 nodes, those networks definitely do not have this property. So you cannot say that network with 6 nodes is critical ordered or chaotic, because criticality is just not there. It's a too small network
in
to see the critical behavior.
In our projecting model, we used 16 nodes.
Yes.
Uh-huh.
And if you can go back to this callback library distance for the unperturbed case.
You mean this?
The callback library divergence in the non-perturbed case.
A callback library divergence.
Yeah. Well, you will see that for the different case, although on average, for k equal 2, you have the highest value, but the error bars embrace all these points, right? So that the point for k equal 1 falls within the error bars of the point for k equal 2, which also falls within the error bars of the point for k equal 3. So this means that you have a lot of uncertainty in this ensemble of networks, right? And this is because some of these networks are critical, but some others are not. And this is because you are using networks which are very, very small to actually see this property clearly. Well, this is what I think. And then the other comment I wanted to make is that in the multi-layer case, you're using the intra-layer networks are 6 nodes.
Yes.
So you cannot see criticality there. You cannot actually amplify this property because this property is not present in these networks in the first place. So probably what you're seeing is the effect of the entire multi-layer network, because criticality at the smallest scale is not visible, not with these sizes. So probably you want to, I mean, even though these results point in the right direction, I wouldn't be too confident of what they are saying because these networks are too small. So probably you want to do these calculations. You will most probably get better results pointing in this direction, but with larger networks, which is actually what we see when we talk about the criticality of the E. coli network. For instance, we're talking about thousands of genes. We're not talking about a small circuit made up of 6 genes, because then, okay, it has a dynamics, but these dynamics cannot be classified as either critical or chaotic or ordered.
Okay.
That's it.
Thank you for your suggestion, comments.
Another option would be to use an alternative measure. So, for example, we have a measure of complexity which is based on information theory, and you could apply it on small networks. And I mean, it wouldn't be criticality, but it's strongly correlated with criticality in random networks for large networks. So if you get high values of that complexity, then you could say, well, it's analogous for larger networks.
Okay.
But yeah, something to be explored. Nathan, what's that? Yep. Better with the microphone so that the streaming can also get it.
How do you correlate the properties of the gene regulatory network with the morphological interconnections between different cells? For instance, if you wanted to correlate the number of positive and negative feedback mechanisms with a certain kind of pattern, how would you do that?
You mean how can I correlate the properties of gene regulatory networks and the morphogenetic
Morphology,
patterns?
the structure of the tissue. You were talking
about. Our model is based on biological evidence, and each cell has a gene regulatory network, right? So the cells in our actually our model is a cell aggregation, and each cell has the same identical gene regulatory networks. And then the cell in the gene regulatory networks, we used the Boolean networks. So there we can get attractors. So we assigned the cellular functions to the attractors. This is the base. There are much evidence that attractors that represent cellular functions or cellular behaviors. So based on the biological evidence, we assigned those cellular functions such as proliferation and the differentiation to the attractors. And then we observed the cellular behaviors.
Okay, so you have to start from actual gene regulatory networks that represent known cells where you can in some way tell when the cell is dividing or when it's attracting or being repulsive towards the other cells.
Mm-hmm.
Any other question? No? Well, if not, let's thank Kevin again.
Thank you.